Hello, I am Erdem from UVision. In this video we will design an half-feather circuit using Quartus software, and the design will be done in Schematic and in Verilog. Lastly, we will test our designs using university program waveform and Modelsim by writing a Testbench. Alright, before designing anything, we need to we need to find a truth table for our outputs in terms of the inputs. So a typical half-feather circuit has two inputs that are to be summed up, and one output that is the sum, and another output is the carry. So by using a K-map or truth table, we can define the outputs, and this website called charliecoleman.com has a good user interface to specify kernel maps for your applications, and let's just do it for our case. In our case, we have two inputs, and let's call them A and B, and for the first output, I will draw K-map for the sum output. Click continue, and here we have our kernel map. So when A and B are 0, sum is 0. When A and B are 1, when A is 0, B is 1, sum is 1. And when A is 1, B is 0, sum is again 1. But when both of them are 1, sum is 0, but there's a carry out. Since it's not the K-map of the carry, we won't deal with that, so leave the last entry as 0. So click continue, and here we can see the resulting expression for the sum output. It's B prime or A prime and B. If you go back to kernel map, we can see a pattern here. Actually, it's a checkerboard pattern. So what's a checkerboard pattern? It is alternating zeros and ones in a row, and this fashion just toggles on the next row. So in the first row we have 0 and 1, but in the next row we have 1 and 0. It's just a 2x2 version of the checkerboard pattern. So why is the checkerboard pattern is important? Because it just maps to XOR logical function. So instead of writing sum as A and B prime or A prime and B, we will just write sum as A XOR B. Alright, by now we have defined the sum output, and we just need to define the carry output. So I'm just returning back to the first step, and I named the output as carry. Let's fill the kernel map. Actually, carry is just 1 when both of the inputs are 1, because sum is 0 in this case, but sum maps to carry as 1. In other cases, there's never carry, right? So I'll just leave the rest as 0. Click continue, and it's actually very obvious that carry is just A and B. Okay, now we have defined our outputs in terms of our inputs. So let's create a Quartus project actually. So you can do this by clicking new project wizard, or by clicking file new Quartus project, and then proceed. So click next here, and here we need to specify our project working directory, and let's do that. So I'm choosing my working directory as here, and inside this directory I'm creating a new folder for our project, and I name the project same as the project folder. Click next. It says that this folder does not exist. Do you want to create it? Yes, I want to. So here we can specify an empty project or project templates that are provided by Quartus. So I'm not interested in project templates. If you are interested, you can check that out. We will just create an empty project. In this window, you can input your previous Quartus related files like Verilog file, like Schematic file, etc. Since we don't have any, I'm just skipping this page. And in this page, you can specify your FPGA model and then the version that you have. Actually, I won't upload anything to FPGA, so I'm just skipping here. And here, our simulation environment is declared as Modelsim Altera, and I will use Modelsim Altera actually, and I will use Verilog HDL for the hardware language. Click next and finish. By this time we have just a blank project that consists of nothing actually. We need to create new things and fill the project up. So firstly we will do the design in schematic file. So for this I click File and New, then navigate to block diagram schematic file, and now I have just a blank schematic. This page does not have any grids or something because I deleted them. You can delete the grids by going to Tools tab and choose Options, Block Symbol Editor, and just uncheck this Show Guidelines because they look ugly. Anyways, click Cancel. I click Cancel, and I will first specify my inputs and outputs. To do that, click this pin tool icon and click Input. I will drop two input pins to represent A and B, and I will drop again two output pins to represent sum and carry. So let's rename those pin names actually. So double click on the pins and rename them. The first one is A, or you can rename that by just clicking on the pin underscore name text itself. So that's B, that's sum, and that's carry. Alright, we have input and output pins. Remember that sum is XOR of A and B. We need to put an XOR gate. How do we do that? We do that by clicking symbol tool icon, and on the name bar we just write XOR. You get the XOR gate. If you don't want to get it this way, you can use folder tree structure. So expand the Altera. Since XOR is a primitive function, you can find it under primitive, and it's a logic function actually. So expand logic in alphabetical order, spot the XOR and place it. We need one XOR gate. Then I place one XOR gate. Alright, let's connect inputs to XOR gate and output of the XOR gate to the output. To do that, you need to click this orthogonal node tool and hover your mouse at the input of the input pin. So hover and click, then drag until you find your destination pin or port, let's say. As long as you see a big rectangle on your target node, you can just release your mouse and the two nodes are connected then. So you can see that you can verify it by just dragging the gate up and down. One bug is here that as I move the XOR gate, the wire connecting A to XOR gate just unified with the pin, unified with the node of B. So I need to delete that. To do that, I'm just zooming in and clicking the wires, and then I click the delete button. So now A is also disconnected too, but I can just reconnect it in this fashion. So alright, that's good. And I do the same thing by connecting B to XOR gate, and the last thing is to connect the output of XOR gate to the node of sum output. Now we have a clean cut. We made the connections, and it's alright by this time. Now it's time for the carry. Carry is the end of logical end of A and B. So if I write here AND and press enter, I will get an error, of course, because AND gates are defined, or let's say specified, by the number of inputs that it has. Since we have 2 input AND gate, and I write AND 2 here, then I get a 2 input AND gate. Here you can see 4 input, 8 input AND gates. So take a 2 input AND gate and place it, then connect the related pins to the input of AND gate. So the same thing, hover your mouse and drag and release. Hover your mouse, drag and release. The reason that here we have a big dot, but we don't have that here, is that I started this wire not directly on the node itself, but just before that. So you see there's an excess wire here. It's an excessive wire. For that we have a big point representing that this wire is actually connected to this input. It's okay actually, but it looks ugly, so I delete the line and I reconnect it again. So now the AND has 2 inputs that are A and B, and let's connect output to the carry. Alright, that looks fine. Now it's time to save the file. Click Ctrl S and click Save. Notice that half_other is the name of our project actually. I clicked Save and it's alright by now. Actually you can just fit the schematic to your screen by just clicking this zoom tool and creating a big rectangle around your drawing. Then you can observe your circuit in more detail. It's time to compile the code, so click this Start Analysis and Synthesis button. It's gonna do the job for you, and on this tab you will observe the logs of the compilation, and you can see the percentage of the current process actually. Now if you expand this bar, you can see several outputs, and if they are all green, that means you are in safe. If there are some I guess yellow texts, that means warning, and red texts mean you have errors. Go and fix them. Alright, compilation is done. Now it's time to simulate. For simulation I'm gonna open a new file, and simulation will be made first in numerous program, so click that. We have a clean interface, nothing is inside. To simulate something, to simulate a logical module, we need to have its inputs and outputs. So I'm going to insert them by clicking Edit, Insert Node or Bus, click Node Finder, and star here means that bring me all inputs and outputs. I don't have any restriction, so it's like a wildcard. Click List here, and here you have your inputs and outputs. So select them all and click this arrow, then you are okay. Inputs and outputs are in the workspace. So click OK. Now here we are. Note that this horizontal bar represents the timeline. Time amount is 1 microsecond. It's too long. I'm gonna decrease that by clicking this Set End Time, and I will change the time unit to nanosecond, and I will make it 40 nanoseconds. Now we must actually we should specify inputs such that every input combination is covered. So click on the first input, that is A, and click this counter. It will count every 10 nanoseconds. Click OK. You see that it alternates every 10 nanoseconds, 0, 1, 0, 1. For B, click count and make the count everything as 20, so that it will change its value in 20 nanoseconds. If you observe that we have input combination of 0, 0, 1, 0, 0, 1 and 1, 1. It's actually what you can get from a 2 input case, 2 to the power 2, that makes 4. We covered every input combination. So to simulate this, click this Run Functional Simulation button. It says that do you want to save it? Do you want to save the waveform? Yes, I want to save it. So click Save, and it's gonna generate some logs, and lastly the output file, output waveforms. We can see that the module works correctly because input combination 0, 0, carry and sum are 0. Carry is 1 only if A and B are 1, and sum is 1 only if either of the inputs are 1, right? Then it's okay, we made a good design, the things are as expected. So close this and close this. We are done with this actually. Now I'm gonna do the same module, half adder module in Verilog, but I'm gonna do that in another project. Actually I could do this in the same project, but for simplicity I'm just gonna open another project. To do that, actually I click File and New Quartus project. It says, do you want to close the current one? Yes, I want to. The same story here. I'm gonna create another folder for this new project actually. I'm gonna copy it and paste it. Next. Simulation language is Verilog. Finish. I'll again have a new blank project that contains nothing, and let's create some new Verilog file here. Alright, it's a clean Verilog file. Now modules are declared in Verilog by module keyword, and then you need to give it a name. Give your module a name. I'll call that half adder, and you need to open some parentheses and put some semicolon after that. And every module must be ended with end module keyword. So between lines 1 and 3 you need to specify the functionality of the module. Inside these parentheses I will specify the inputs and outputs of the module. Actually we have an input called A, we have an input called B, we have an output called sum, and we have an output called carry, right? In Verilog it's safe to specify the type of the input. Actually this module, half adder module, is a combination of module, right? Combination circuit. Then the input type is wire, right? It's not a register, it's not type of reg. So B is also wire, output is also wire, and sum is also wire, and carry is also wire. What I like when declaring the input and output pins, I like them in a separate line, each of them. So I'm just for this purpose gonna declare every input and output in a new line. Alright, inputs and outputs are declared. Now time to specify the functionality. An output can be assigned to represent a specific function by assign keyword. So I will assign sum XOR of A and B, right? So you can do that by just writing a caret b. Caret means in Verilog logical XOR operation. Then what is the carry actually? It is the end of A and B, right? Then A ampersand B is directly the end operation, logical end operation of A and B. Now we are done with this. Save the module by Ctrl S, save it and just compile it, of course. It's gonna compile with the process here. The report is given here. Okay, it correctly compiled it. To test this module, I won't use the universal program file. Instead, I will write a testbench code. Why do I do that? Because we already demonstrated the universal program file usage, and it's time to write some testbench code, right? Okay. So a testbench file is also a Verilog file. So I create file new, a new Verilog file. Testbench files has also names called modules, and I'm gonna give this testbench the name half adder test, and end this module with by writing end module. Note that testbench modules have no input or output pins specified, so I'm gonna just leave blank the inside of parentheses. Inside the module, I'm gonna declare the connections of wires that drive the target module. So I'm going to declare here some wires or registers that drive our target module, that is half adder. So I'm going to specify them with reg actually, and call them A in and A B in. Alright, and output should be observed by a wire variable. Then it is some underscore out and carry underscore out. So declaring A and B inputs as reg just lets us to hold their value for a certain amount of time. Alright, then let's declare our module that we designed. So it's called half adder, right? So I'm gonna give the module base name as half adder, and I'm gonna create an instance of that, and I will call that half adder underscore DUT. So that means device under test. Actually, the input, I'm gonna connect the A input of the half adder, A underscore in, and B input of half adder, B underscore in, and some input of the half adder, some underscore out, and carry is connected to carry underscore out. Okay, now we can derive half adder instance with these variable signals and observe them from wires carry out and some out. Okay, the purpose of this writing test bench is to simulate something in an autonomous way. Instead of giving signals by hand, we will just write them in a text file and read those lines into the testbench code. So we do that by at the initial run of the program, initial run of the testbench. So write initial, begin, and end. Initially, I will read some memory, right? Then the keyword is read memory. We will specify the input as binary, so I put here a B. So it's read memory binary. If I were to write it in hexadecimal format, I were to write here H. Sorry. So it's like this. Put a comma. It has two inputs actually. First one specifies the directory, and second one specified. Okay, you read it. Where do you want to store it in the test bench? Alright. First I will give the directory of the file. Right? Then I will just grab a test vector file from my previous works. Like I'm gonna grab this, it doesn't matter. Go back, open half header, and I put it here, and I rename it to half header test vector. Here we will specify our input combinations actually. What were they? We have two inputs, and they are zeros. They can be 0, 0, they can be 0, 1, they can be 1, 0, and they can be 1, 1. Why I put underscores here is that it increases readability. It's ignored by the Quartus or Verilog, whatever. So first column represents A, second column represents B inputs. So save this. And actually the directory is given here, so you just copy that and paste it here. Note that these slashes are backwards. Instead they must be forward, so replace them with forward, and just the forward, and inside half header we have half header test vector, something like this, right? Yes, and the extension is .tv, test vector. So note that it's an array structure actually. So array index 0, 1, 2, 3. We need to have some array inside the test bench, and I'm gonna declare that array here, a register of array of width 2, right? Because we have 2 bits here, 2 bits, and I'll call that test vectors. And note that we have 4 entries here. Then I'm gonna initiate 4 test vectors of width 2 in this syntax. So reading destination is test vectors. Alright? Good. We need to find a way to address specific element of the test vector. So we can do that actually in for loop later. So I'm just gonna leave it right now as it is. And I'm going to declare an always block. So this always means that execute whatever inside this block always, like infinite while loop. However, this initial means that at the initial run, just run this once, alright? Not infinitely, for once. So what we want to do always is iterate through the test vectors that are provided in our file. So to address some specific index of the test vector array, I'm going to create a dummy variable called integer I, and inside this always loop I'm gonna create a for loop to iterate through every element of the test vector, and so that we can try every combination of inputs. Here I initiate a variable as 0 and I declared it here as integer. I is less than 4 because we have 4 elements, and every time increment I as 1. Okay, now note that we concatenated the bit values of inputs here. So 0, 0 is a concatenation of 0 and 0, like 1, 0 is concatenation of 1 and 0. Then we will specify the inputs in a concatenated way, like this. Curly braces mean concatenation. So what does it equal to? It is equal to vectors of index I, right? Ith element of the test vectors. By this time, I applied A and B inputs, but to observe them, I need to wait for some time. And delays in this test bench are specified by hashtag number, and I put 10 units of delay here. Note that I'm just iterating through every test vector, and I'm waiting 10 nanoseconds or whatever picoseconds to observe them. So let's save this, and I'm gonna name this half adder test bench, or let's copy this name and save it like this. Okay, let's compile it. One important point to note that is the testbench file must be inside the files of the project. So you might write your testbench file in another text editor, but don't forget to place your testbench into your project files. See that compilation is correct actually. Now we can open Modelsim and simulate our design. Before navigating to Modelsim, I want to show you something. Since we have written a Verilog code here, we can see the output hardware that it is translated to inside the Quartus. It is done by just clicking Tools, Netlist Viewers, and RTL Viewer. So you see that Verilog translated our code that is written in here to this hardware. Carry is AND operation of A and B, and sum is XOR operation of A and B. So that's fine. Close it and open Tools, Run Simulation Tool, RTL Simulation. It's gonna take a while. It will open the Modelsim. Alright, so what do we see? Here is a chaotic window, big window. On the right hand side we see our waveform observation panel. On here we will see our input and output pins, and on here we have our workspace. So to import your test bench into Modelsim, click compile, and go backwards from here. Backwards. Find your testbench file. It was half_test. Click on it and click compile. Here you see the compilation log. It has 0 errors, 0 warnings. So click done. Then expand the work directory here and click half_test. It has an error actually. So what it says is unresolved reference to read memory binary. Actually I forgot to place a dollar sign here because it's the syntax of Verilog. I'm going to close it. Yes, I want to close it, and I'm just going to place a dollar sign here. Yes, dollar. And I'm going to save it and compile again. So when you change something in your Testbench or module, don't forget to recompile everything to observe your things in simulations. So what we can note here is that compilation time, the Quartus did not raise any error regarding this dollar sign, and it compiled successfully, but Modelsim just pointed that out. So to make sure your designs, I really recommend that you go and check your designs in Modelsim. And another mistake here is the quotation marks here, so just remove them also and recompile, please. I hope this time it will be success, hopefully, and I'm gonna observe the log here. Alright, everything is under control right now. So click Tools and RTL Simulation to open Modelsim. I'm going to recompile the Testbench inside the Modelsim. Click Compile, Compile, Back, and Testbench. Click Done. So it has again 0 warnings, but the error may raise when importing to Modelsim. Click, double click, and alright, this time nothing bad. We have our inputs here, and just select them all and just drag them into your waveform observation panel like this. We have placed the signals, and we can run the simulation with this button here. I click this, and we can observe the signals here. Note that the window is too big for this observation, so click somewhere inside the waveform panel and just click F to focus on the inputs. Alright, so what do we see here? Let's observe. We see that we have I test vectors carry out sum out, B in and A in. These are just related to Testbench, not at all related with the module itself, so you can ignore them, and we can observe the input and output. I'm gonna zoom a little bit by clicking this plus button actually. Note that when A is 0, B is 0, sum and carry out are 0. That's fine. When A is 1, when B is 1, A is 0, sum is 1, but carry out is 0, that's fine also. When A is 0, B is 1, sum is 1, carry out is 0, that's fine. And when both of them are 1, note that sum is 0, carry out is 1. So this is a valid design. You might ask that we specified 4 inputs, but here it's like 8, more than 4 outputs. More than 4 input combinations. The reason is that even though we have here 4 input combinations, simulation runtime is 100 picoseconds. So if I do this simulation for 40 picoseconds and I restart the simulation, so you can clear the simulation by clicking this restart and click this run again. Now you can see that oops, and typo here. Now you can see that you have only 4 input combinations and the simulation is ended here. Alright, that's all for this video. Actually, it's a very introductory video to Quartus, Verilog, Modelsim universal program file. If you like, please subscribe and thumbs up. and don't forget to recommend this to your friends. Bye.